Hello, Mike. I think we're live.
Yes, we are live, and welcome to those that are connecting at the moment. I'll wait for people as they come on. It's a big session today, and I'll make the introductions once we think that everyone's in.
Okay, we're ready to start, Mike.
Okay. Right, well, it's past 6 o'clock, and that's the starting time for our webinar today. Very warm welcome to everybody to this webinar on technology advancements in lightning protection by de-ionization. My name's Mike Frayne, and I'm the Fellow of the Institute of Engineering and Technology and the Secretary for the South Yorkshire Local Network, who are responsible for running this webinar, and actually several other webinar events, virtual events that we've carried out over the last couple of years. I'm proud to volunteer for the Institute. That's given me so much over my long career, so I'm very happy to recommend volunteering for you wherever you are in the world. For those who aren't members, you'll be joining one of the most prestigious professional institutes with over 158,000 members across the world in 153 countries. So before we start, just a few house rules. Before we commence with the presentation, please feel free to ask questions at any time. Our speaker will endeavour to answer at the end of the presentation and not during the presentation itself. Should we run out of time, the Q&A session will be carried out afterwards, and we'll gather all the questions together, and they'll be posted on the South Yorkshire Local Network site. That will be in the chat function, actually, the site address. So make a note of that if you want to follow this up. And it is being recorded as well, so you'll be able to watch again afterwards. That same site, the local network site, will give you information on how to obtain CPD certificates. So anybody that needs to have a CPD certificate, you can go through that site and get it from there. So that the address will be posted into the chat function. So don't use the chat function to ask questions, as we can't download a copy. So if we do run out of time, we won't be able to get a copy of your question if we've not answered it. So here we go then. Let's get on with the show. Earlier in this year, I was invited to a substation conference in Leicester when I first heard our speaker for today, Stephen Horsley. He talked about the subject of stopping lightning strikes by de-ionising the atmosphere using the invention of the great Nikola Tesla from 100 years ago. I was fascinated then and very much look forward to hearing from Stephen today. He has over 40 years in global sales and technical management in the electronic and electrical industries, and he is Certec Sales Director for Europe, Middle East, Africa and Asia. And is also a Director of Global Sales at IPEC UK, who won the Queen's Award for International Trade in 2016. He is a member of our own Institute of Engineering and Technology and also the IEEE. In addition, he's a member of the power and energy sector for the IEEE and a member of the Seagrey International Council on Larger Electrical Systems. So without further ado, let me hand over to Stephen. Welcome, Stephen. The floor is yours. I noticed that you're not sharing the screen now, so if you can share your presentation.
Yeah. So, Mike, first of all, thank you. Can you hear me okay?
Yes, perfectly. Thank you.
It's saying on my screen share that we'll be able to open that up now. So let me do that, which is good. We go into presentation mode, and hopefully everybody can see it. So thank you very much indeed.
Sorry, Stephen, just go into slideshow.
Yep. Apologies, everybody. It's not allowing me to do that at the moment.
Can you see it at the top of your screen there?
Yeah, I can. Yeah. Say mute, stop video, participants chat, new share.
Yeah, no, not up there on the strap line of your actual presentation. There should be it says file home in, so that's it, and then just change that display settings. Yeah,
okay, show taskbar.
So just the one next to it, go to display settings, the one next to it.
Yeah, I'm sorry.
That's okay. That's okay.
Excuse me, everybody. We'll get there in a second.
That's okay. Just click on that display settings next to it at the top there. You see the little drop next to it, next to where you are, next door to that show task. There's one that says display settings
on my screen.
Because otherwise we can see your notes next to it.
Well, yeah. Unfortunately, it's not showing that.
Okay.
Yeah. Okay. I think just for the purpose of where we are here, I cannot get that to go to full screen at the moment. Let me just see if it does it here. No.
Yeah, go to that again and hide presenter view.
Okay. It's great we've got an expert here. Thank you very much.
That's it. There we are. Perfect. Good
luck. Okay,
luck.
Once again, my name is Steve Horsley. Thank you very much, Mike, for, first of all, this opportunity to speak to the members of IET, the Institution of Engineering Technology, of which I became a proud member of very recently. My background is I've been in the electrical and electronic industry for a very long time, it seems. And what we're going to talk about today is lightning protection technology and the advancements. And I think for quite a lot of people, you may not be aware of the de-ionization technology that's around. So just one quick slide here about the company. The company is called Certec. It's based in South America, in Paraguay. South America has a lot of lightning activity, and this is just some of the people. There's over 100 employees in the company. Mr. Schiffarelli, who's an electrical engineer, is in the white, and his partner, co-owners of the company, are there as well. They've been protecting against lightning strikes for the last 21 years. They're an award-winning company, highly thought of in South America and North America. They do a lot of work in telecom sites, in grounding activity and so on. So let's talk about lightning. And first of all, before we get to de-ionization and ionization, let's just look at a few of the factors that we've got here. So what it's basically showing you on the slide here is, an intelligent lightning protection technology. Of course, for nearly 300 years, we've had lightning protection technologies in the world. And we're going to go through some of those and talk about the different technologies and why de-ionization is a good technology. We're going to start, if you've got some sound up, there's going to be a few flashes and bangs. There's no reason you shouldn't start a lightning protection webinar without some activity. So hopefully this video is going to play. What we're seeing here, and I'm sure that every single person that's on the webinar today has seen lightning, hopefully not been too close to it. But what we see is this electrical activity in the clouds, in the time-lapse video here, where it's just a frenzy of activity. I mean, the thing about the lightning is you really have no idea where it's going to go. And as you see by all of these streamers that we see going, and I'll explain that a little bit more in a while, the lightning activity is going in multiple different directions. You see some flashes that are going to the ground. You see some that are just going through the air. So it's quite an activity, and I know that everybody's seen that. So how do you protect against this? How do you get to a position whereby the assets that you're trying to protect are safe? So this is what we're going to talk about in today's webinar. So before we get into the technology, we have to talk a little bit more about lightning and the formation of lightning. So lightning is, if you understand that if you're learning about lightning, the term is fulminology. If you're frightened about lightning, which a lot of people have been, especially when you're young, it's called astrophobia. In the UK, if I just look at the UK market for the moment, the Met Office says that there's about 300,000 strikes every year in the UK, which is a significant number. And when you think about 300,000 strikes, there's a chance that one of them is going to be pretty close. Globally, though, the fact is much higher. It's about 100 strikes every second recorded. And we know this data because of lightning detection centers that are placed all over the world. A typical strike can be 100 million, 300 million volts by the National Weather Service telling us that. And so that's a lot of volts. And then we have the current, which of course is the dangerous part, which can be about 30,000 amps. A lightning strike is said to travel around 270,000 miles an hour, 430 kilometers per hour. So we know when we see a lightning strike, we've all seen them when they discharge, they are going at tremendous speed. The one thing that you get with lightning as well, of course, is when these ionized plasma channels are coming down towards the Earth, is this significant temperature. So what we see with a lightning strike, which everybody knows, is that we've got high voltage, we've got high amps, we've got tremendous speed, we've got temperatures up to 30,000 degrees. And we also get another very unwanted aspect of it all, which is an electromagnetic pulse and radiation. So when we look at lightning, what we see is all of these, these aspects, which if the lightning strike is coming to you, is bringing all of this with it. So just looking at this chart here, you can see this jiggity-jaggedy line coming down on the right here with these branches. And you can see on the little picture in the middle there that a bit like when we're flying, in aircraft and you've been through a bumpy zone, the air is not completely constant. Everything about the air is different. We have cool air, we have dry air, we have dense air. And lightning is generally looking for the path of least resistance to be able to neutralize itself and to come back. What this says here is types of lightning. So we have intra-cloud lightning. This is lightning within the cloud. We have cloud to cloud, so different clouds of lightning. We have the most dangerous one for us all, which is the cloud to the ground, or it's actually cloud to sea. We also have the opposite way around. Lightning can go from the ground up to the cloud. We also have a thing called a bolt from the blue. And in fact, this picture is a little bit like a bolt from the blue because the actual discharge can occur many, many miles, kilometers away from the actual cumulonimbus cloud, and a strike can occur. And these are very, very difficult to predict this type of a lightning strike. Way above, up in the upper atmospheres, there is also lightning. There are L's, there are red sprites, there are blue jets, there are different types of lightning that's way up. Collectively, these type of lightning events are called transient luminous events, and you can see them way above the cumulonimbus cloud. What we see in this picture is, in the background here, is the cloud is a cloud which grows to significant height. These clouds grow way up into the atmosphere, and the convection from the hot air and cold air is causing these cloud formations, and they become extremely turbulent. In this particular video I'm going to show you, and I'm going to pause it hopefully as we go along, is now we're seeing a cloud and we're seeing charge. So what has happened is the cumulonimbus cloud and the ice crystals and the water vapor is in such a frenzy that it's actually affecting the atoms, the molecules, And it does what it says is it knocks off one of the electrons, and those electrons become free electrons, and we'll have a look at that in a moment. So I'm just going to credit Picos Hanks, because you can see this video on YouTube. It's a brilliant video that he put together just to show how the charges are moving around in the atmosphere. And what we see there is the positive and negative charges becoming split. The electrons and protons become split, they become electrically charged. And as everybody on this call knows, the basics of electrical law is that two opposite charges will attract each other, two similar charges repel each other. And so what we see is in an intracloud scenario here, these step leaders, these plus and minus symbols going through the cloud, and all they're trying to do is to find the greatest attraction and to come back to a neutral state. As the video goes on, we now get to the dangerous side, where we see step leaders going down to the ground, or it can be the sea, and they're discharging to the ground. What you see on the video as well now is these step leaders coming down, and you see this significant buildup of opposite charge. So we've all held magnets, I'm sure, and when you hold magnets of similar polarity, of course, they push apart. So these negative streamers that are coming down from the cumulonimbus cloud have pushed the negative charge way into the ground. And because of the attraction of opposite charge, the positive charges are now coming up. What we see here is the discharge occurring. Now, lightning has a thing called a return stroke, and it can be 1 to 20 times that we can have the return stroke. What you're seeing is step leaders in this particular part of the video here. I'll try and well, this one here, I'll show it more. You see this step leader coming up from the top of a telecoms tower, meeting the downcoming streamers, which are probably negative charge, and the tower was positively charged. And of course, we get that discharge. And you see that in these significant lightning strikes that we see in this particular video. You know, lightning travels at such speed, it puts out an electromagnetic pulse. It's the sound wave that we hear, and then we see the flash of lightning. We know that the difference is between light and sound. And so again, you see our streamer going through the atmosphere. It's going in all sorts of different directions. It's quite a crazy thing. And on the right-hand side, you see a lot of electrical activity as well. So the video here is really showing the differences on the what is called streamers, positive and negative. And remember, we talked about magnetism and the repulsion of similar charges pushing the other charge into the ground. So when we see lightning strike, wherever it is because of a buildup of charge. This is a very good website. It's called Blitz.org. It's live data. When you click, there's a link here that everybody can click on. You may have already seen this particular website. When you click on it, you can actually see globally lightning strikes as they're happening, because they're being picked up by detectors around the world. And what we see on this picture is that, normally when we're near thunder, we normally maybe see, a few strikes or maybe quite a few strikes. But this particular map shows that in regions, if you look up here near Finland, in fact, let me just put my pointer on here. Pointer options. Okay, if you see up in Finland here, it's a little bit difficult to see, but in this area here, in these circles here, there was 3,100 strikes. Down here towards Algeria, 124 at the time I took this shot, and up towards the UK, actually out into the Atlantic Ocean here, 27 strikes. Across in Australia, you see a huge amount of activity. And of course, if you look at this site, generally in the Gulf of Mexico, you're going to see lightning strikes every day. This website does not cover completely South America and South Africa and places like that, so and China. And so there are more strikes that we see, and that's why we get to this 100 strikes per second. So it's a great site to look at. Take a look at it. Go to Blitz.org and you'll see it. I was doing a seminar in the Midlands at the beginning of September, and what was staggering was that we had in the United Kingdom, in the space of 1 week, 36,000 lightning strikes. It was a truly active week. And what you see on these pictures here is you see a little sort of breakdown when I took the snapshot here in the Midlands, 606, and Northern Ireland 17, and then right across Europe. It was an extremely stormy day. On the right-hand side top picture, these are new build houses in Wales. And as you can see on the 5th of September, that one on the right-hand side got hit. The people across the road had a camera which just happened to be running and caught this strike going to the house. So considerable damage. And again, down in the bottom here, another snapshot at a different time where you can see the amount of lightning strikes. So the chances are with 36,000 lightning strikes, somewhere in the UK, you might have been close to them. So when we talk about atmospheric ionization, it can happen in many different ways. Sometimes cosmic rays can achieve this. And of course, what we know in a cumulonimbus cloud is it's said that the ice crystals and the shear activity in the cloud can move electrons away from the atom. And these become free electrons. And then what we start up having is an electrically charged atmosphere. And as we saw in the video earlier, the electrons and the protons have moved apart, and their first job is to come back together to neutralize themselves. So it's a basics of what happens there. So just looking at this before I put the words up, of course, there are a lot of technologies out there today to help us protect against lightning, and they all work to a certain way. And in fact, as we know, I think most people have seen in their lives the kite that Benjamin Franklin put up into the sky. He was exceptionally lucky that he didn't end up being electrocuted, but he found out that that lightning was in fact electricity. And he wanted to make people safe. And way back in 1752, he invented what everybody, I would think, on the cool nose is the Franklin rod. And these are deployed all over the world. And the idea of the Franklin rod is to allow an area where if a discharge is coming, it will come to the Franklin rod. And as you can see in the picture below here, it's really just taking this charge safely to ground. So it's not, say it in the best respect, an intelligent technology. It is a building up of the ionization of the opposite charge within the Franklin rod. What we see on the right-hand side is an invention that came from France and is deployed as well across the world. It's called an early streamer emitter. And the early streamer emitter as an electromechanical exciter. And the idea of this technology is to fire an upstreamer into the atmosphere and to capture a lightning strike before it targets anything else. So these technologies are very similar. Franklin rod, they are also ionized technologies, and the one on the right here is firing up this upstreamer. It could be considered dangerous. It could be considered whether or not that this technology works fully. I know that it's been around now for 30 years. So this way, with these two technologies here, that you will get a lightning strike come to them if possible. What we see down the bottom as well now is another technology which is around, and this is called a dissipation array system. This technology is quite clever. What it does is it tries to confuse the atmosphere and de-ionize it by having multiple points, as you can see on these brush-looking rods here, and you can see some quite big structures above these buildings here. What we see about these, though, is that these are quite large structures, and when you go into the dissipation array systems more, the structures of those systems can be very wide, different, to be able to provide protection. So the idea of this is that you do not get a buildup of charge, but of course we have a different type of technology here. So the dissipation array system, again, is something that's out in the market and is deployed. So, sorry, I've got a bit of my bar at the top here, but everything changed back in 1916. Nikola Tesla, the brilliant Nikola Tesla, which we all know, said that, you know, he was fascinated by lightning. He was said to be born in a lightning storm. He said that the Franklin rods and this type of technology was a danger to society. Instead of protecting people, you are now creating a path for the lightning to come quite close to you, albeit that it can take the strike and take it to ground. But when you do have a strike, remember that slide at the beginning where we have the amount of volts, the amount of amps, the temperature, the electromagnetic pulse, albeit for, you know, milliseconds of time, you do get all of that come. And there are projects like for schools where they do not want to put this technology on top of their school buildings, because the last thing you want to see is a lightning strike come into it. So what Nikola Tesla did, because he was so brilliant, back in 1916, he thought out of the box. He said, if you take away the ability for the buildup of charge, you cannot have a lightning strike. Because as we've said, it's this buildup of positive and negative charge. And if you neutralize, de-ionise the atmosphere, you cannot have a strike because there is not enough charge. It doesn't deflect lightning. All it does is protects an area, and lightning will be drawn to wherever the buildup of charge is. So his technology, which he patented way back in 1916, 1918, was this device called a PDCE. The first thing you see about this device is it's this cylindrical type of shape here. It's not a point. And what he did with this technology, which is a passive technology, is in the very early days of 1916, this technology actually did deionise the atmosphere, but perhaps not to the levels that we do today. We know Tesla invented the Tesla coil, alternating current, 700 other patents. And what happened with this technology is you see on the patent office here, his original drawing on the right-hand side, you know, painted it in New York. And patents, as we all know, in the world last for a period of time. And very unfortunately with this technology, back in the 1930s, the patent ran out, and in fact it got lost. The patent was lost in archives, and by chance, Mr. Schiaparelli, the president of Certec, came across this patent by reading articles and exploring, and could see that this technology was completely different to Franklin rods at the time, and also the newer technologies of ESE and dissipation array systems, that it's a singular device. And Tesla in his early days, you know, picked on different shapes and sizes in his experimentation. So what happened was Mr. Schiaparelli, when he found this technology, decided that this is a product worth building. A product that can de-ionise the atmosphere, and a product that can protect different areas. What you'll see with this technology is inside of here is a capacitive technology that allows the ability for the charge in the atmosphere to be drawn to it and safely to ground. What happened last year, out of respect to Nikola Tesla, was that myself and the team at Certec went to the Tesla Institute. I didn't actually go, but my colleagues did, and took this device and said, look, this was an invention from Nikola Tesla. Can we prove this technology in a modern day product? And can you certify this technology as doing exactly what Nikola Tesla set out to do? So the laboratory, over a period of time, took the devices in, did impulse generation pulses. You'll see this a bit later on in the presentation. And in fact, this case study that we see here, number 322053, which is available for people to view, certified that Certec had taken the technology of Nikola Tesla and turned it into what is now a modern day globally deployed product. This one here has these ball type effects here. You'll see this in the video at the moment. There are different shapes and sizes, and they don't all look like this. They look different, some of them depending on what you're trying to protect. So now let's look at the functionality of this technology and what happens. The principle is quite simple, but it's a complex technology inside. it's using capacitive technology, and these are very, very specialist capacitors, which are inside of here. And I know a lot of people here are engineers. You're going to know everything about a capacitor. So what is so clever about the technology as well, it requires no power. This works off of nature. It actually, with the earth lead that goes from the CMCE down into the ground, it actually knows the polarity of whether it's positive or negative. And then inside of the device, the capacitive technology, floating electrodes and so on, actually determine how the atmosphere should be drained. So it requires no power. So this device is superb for the world. All of these devices are completely recyclable as well. So it stabilizes the electric field. It creates a shield. It doesn't deflect lightning. It's just protecting the area that's in, because as I said just now, what it does is it takes away the complete ability for a buildup of charge to occur. And this can be draining of the current in harmless milliamps to ground. In fact, usually in the older days of the early technology here, a clamp meter was used to go around the earth cable and just take a reading to make sure the technology was working. So it eliminates the formation of lightning because it does not allow it. It's de-ionizing the atmosphere. It's bringing the charges back to a natural state. So the capacitors have their electrodes referenced to the grounding system, which is same polarity. You'll see that in the video in a moment. And there is a free electrode which induces atmospheric charges of opposite polarity. So this is the clever part of it. When you look at this building here, now we have a change in protection technology. As I've already said, there is the Franklin rod, the ESC, and the dissipation array system, all different ways of protecting against lightning. Again, we have the cumulonimbus cloud here, and the bottom of the cloud is full of electrons, which are creating streamers, which are looking for the buildup of charge, which is on the ground. So electrons, of course, negative, and protons positive. And it depends on the air permeability, the dielectric constant, the electrical resistance, and a number of other factors that allow this technology to work. So according to the potential difference which is created inside the CMCE, we get a balancing de-ionizing effect. And as I said already, the charges are taken to ground. So that is, in basics, the principle of the technology. Again, obviously, electrical law 101, negative and positive charges attract, and similar charges repel. So lightning is just trying to neutralize itself in either direction. So now let's just look at this device and what is going on inside of it. So the loads that come from the ground are distributed in a floating electrode to be charged with loads of the opposite sign, which is what you can see here. So the bottom part of the device has recognized that the Earth is positively charged and has taken that charge to the bottom part of the technology. And now we see that the buildup of electrons that are in the atmosphere are coming towards the device, but no way is this a buildup of positive charge because of the device shape. And this is what Tesla invented back in 1916. If this was to be a point, you would end up looking like a Franklin rod or other technology. Walter Lewin, I don't know if you've ever seen any of his lectures, he does a phenomenal lecture on YouTube about charge buildup in positive pointed areas. So I'd highly recommend people looking at that. So now we're going to go through what is actually happening and how these charges are coming together. And I'm going to go to seeing here that the top half here is negative, the bottom half is positive. And as the charges are drawn together, they're being taken to the ground safely. The positive charge collects the negative charge in the capacitive technology inside and drains it to ground. The technology does it in 360 degrees. And these devices, this technology of de-ionization goes in different radius from the middle of the device. So it's a bit, I suppose you could refer to the technology like car engines. You can have a 1 liter, a 1.5, 2 liter, 5 liter. So depending on the design internally here, the electrical current drainage is dependent on the size of the capacitive technology that is inside of the device. So the greater the technology, the greater distance that you can actually drain from the atmosphere. And there is a lot of papers and studies on this and documentation to show how this charge is being drawn from the atmosphere and why will it protect these distances from the center of the CMCE. Here we can see a very good example of a CMC installation. This is an example of the National Hurricane Center in the United States of America. What you can see on here is these three circular areas. So one device will cover 25 meters. So you can see the area that it will cover. So in fact, here it's not covering the complete area of the National Hurricane Center. If you go to one of the next devices, which is a 55-meter device, again, it's not covering the complete area. And then when you go to the green one, what you can see here is this huge area that this one device can protect. And if we were to look at traditional technologies, a lot of traditional technologies, you would need maybe Faraday cages. You may need on a building a Franklin rod on every corner. You may need a Franklin rod halfway down. You may need a lot more of the current, the older technologies to protect an area. So bearing in mind that one device here, this green one here, is protecting 120 meters in radius. So how do you know it's working? So the slide at the very beginning talked about intelligence, and this is where intelligent lightning protection has gone to a new level. The company this year said, well, look, we've been installing this for 21 years. We've never had an incident, and periodic testing has been done of all of the installations globally, which is part of the installation process. And as long as these tests are done periodically, you knew the device was working. So from my background and in the electronic industry, I said to the company, why don't we make it even more intelligent? Why don't we add an accessory that allows you to now see that you have electrical current drainage, which you can see here on the laptop. You can have temperature, atmospheric pressure, humidity, height above sea level. And there's even an area, which is actually not showing here, apologies, that shows a recording of lightning strikes within a 30-kilometer radius of the installation of the CMCE. So now what has been happening over the last 6 months, I would say, is that the insurance companies have now really looked at this technology significantly, because you can get reports and you can get alarms. And if you've got many CMCEs protecting an area, you can see that you have this protection in place. As I said, electrical current drainage, and this is running constantly. The atmosphere is never the same. So the current drainage is just constantly changing, as we know. What it does as well is that the future will see the prediction of lightning from this technology as well. So the entire system becomes extremely intelligent. So real-time remote monitoring of your lightning protection. As you know, with Franklin rods, you do not have that. With ESC, they normally have lightning strike counters. I'm not very familiar what dissipation array systems do, but with this technology, you get the whole lot. And here on Google Earth, this is only two. This is at the headquarters in Asuncion in Paraguay. You see two sites. If you click on these, it brings up the complete detail of the protection. What we've been finding as well with the technology is there are some very tall buildings that are around it. And the technology has been starting to see buildup of charges on some of these buildings in the area. And we hope to explore that a lot further as we move forward. To advise the owners of these assets, you're a pretty big target for a strike. When the technology is deployed, of course, there are site surveys. There is a look at what assets need to be protected, site drawings, Google Earth pictures, existing earthing, what is the earthing like, what is the soil like, all of the considerations you have to have for earthing, and then plans are developed. It's very difficult to see, I think, but you can see some yellow circles here. This is quite a large plant in the world, and it required 5 yellow boxes, and 1 hypercritical part there, 1 other. This site would typically have, multiple Franklin rods that would have been there. So the technology comes for different protection as well. So nano, as we've already seen, is a technology that de-ionizes the atmosphere in a radius of 25 meters. This is for, small areas. There's a brilliant video on YouTube where we protect lifeguard huts on the beaches in Florida. Because in Florida, like many places where it's thunder is, lightning it comes in very quickly, and the lifeguard huts, the lifeguards are usually the last guys on the beach, and so we protect a lot of lifeguards hut. And there's news stories, new channel stories on that. Home is typically a home, unless you have one bigger than 55 meters. This will protect the home. Here we get to much larger scale now, 120 meters. Remember, the capacitive and the technology inside it here is increasing to give you this coverage. And then on the right-hand side here, even more technology, which is for areas of high resistance. Sometimes the top of chimneys become extremely hot. And chimneys are usually quite a big target for a strike. And so this technology will protect up to 400 degrees above a chimney. The other approvals that the technology has borne, we're talking about this de-ionizing technology, is it's Underwriters Laboratory approved. It's got the UL 96 certification. And so that is fully certified for the use as on buildings, large complexes, mining boats, power stations, etc. We also see around the world, different ground conditions which are quite corrosive, atmospheres that can be corrosive, especially in some industrial plants that are still around today that haven't been changed. So there is a high resistance technology which is made out of steel and other materials. The company protects a lot of mines, because a mine, when a lightning strike comes by, can actually cause quite a lot of damage for a mine. You imagine some significant strikes above ground, you never know what that effect can be. So this technology here is an anti-vibration device. The technology has moved significantly forward as well, because we have a device called a CMC graphene, and this is for military applications. So the military around the world now are starting to deploy this technology because they, again, want to move away from, the older technologies, those that bring the strike to them. They do not want that. So usually these are all under non-disclosure agreement. There is one picture I can share later. And then on the right-hand side, we've just started doing trials for wind farms, because the rotors and the blades, they are significant targets. So this Twin Max is really like your V12 car engine. This one is extremely powerful, and we're in trials, and we're going to see and hopefully have that technology working. The technology not only protects everything on the land, the technology actually protects everything on the sea. In fact, I don't have a slide here today, but we have a guy called Ian Herbert Smith. He's on the Golden Globe. He set sail just over a month or so ago, 9 months at sea going around the world, and he's a very lucky guy because he's got one of our devices on top of his yacht, which is called Puffin. And the problem when you're at sea is that you do not want the strike to come to your boat. And if it's a single sailing hull boat, a catamaran, a super yacht, a cargo ship, a fishing boat. So this technology is changing things, because the earthing goes down to the hull of the boat, and it provides exactly the same protection as it does on land. So how do we prove this technology? We already talked earlier about Nikola Tesla, his brilliant invention, and the company going to the Tesla Institute in Belgrade, Serbia, and doing the case study to prove the technology further, albeit we've been in business 21 years. So the functionality test is done like this. And this is done with a lot of lightning products. Franklin rods and ESE technology is tested in this way. This is the ITE lab in Valencia, Spain. It's one of the largest labs for this type of technology in the world. What you see above it here, with my highlighter will show, is this artificial cloud. So anywhere within this artificial cloud, a discharge could occur. It could be anywhere here. What you see at the bottom here is the CMCE, and it's earthed and checked. But before you go through testing the CMCE, what you need to do is to have a reference. So a Franklin rod is put here, or an ESE is put here. And as the impulse charges are increased, a discharge will go to the Franklin rod or the ESE, because that's what the technology is there to do, to take the discharge. So now, as we increase the discharge here above the CMCE, in the laboratory, there is no discharge. So the question is, where has the discharge gone? Well, it hasn't actually gone anywhere. It could look for somewhere in the lab, and I know the lab guys were a bit worried when we got up to the voltages we got up to. But the CMCE goes through exactly the same impulses that the Franklin rods and the ESE did, and there was never a discharge from the artificial cloud. This is a bit of an eye chart. Apologies for that. When you look at British standards with Franklin rods or ESE technology, it states that you need to be around 425 to 468 kV in BS 62305. And what we did is we took the lab to its absolute limit. So we went up to 840 kV. Nobody else has done that. And we had absolutely no discharge to the technology. And of course, as we spoke about earlier, the voltages and amps coming from a lightning strike are significantly more than that. But in this technology proving of what the lab could do as the program voltage increased, you can see on the right-hand side here, all these zeros. If there was an X, it meant there was a discharge. So change this chart with the Franklin rod or ESE and you see all the X's. So this now with the ITE lab, proved again that the technology of de-ionization, of balance in the atmosphere, actually works. And then you can have these artificial cloud systems, smaller ones for testing the product. And as you can see, I think this is about 13 centimeters away, build up of impulse charge here, CMC directly underneath it, and no discharge. There is a video. I don't have it today because of the time we have. It's a video that shows a Franklin rod next to a CMCE. They're separated, of course, and the Franklin rod discharges are occurring all the time. As the voltage increases, nothing happens to the CMCE. So in terms of global certifications, let me talk through that for you. In the standard BSEN 62305, the technology meets everything except for one aspect of that standard. And that is the standard states that you must, take a charge and take that charge and safely take it to ground, which is the Franklin rod ESE type of technology. Of course, this technology of de-ionization is not as yet written into the standard. So every aspect of the technology is tested with that one caveat. And I hope over the next 1 to 2 years that this can then become part of the standard or a separate standard within British standards and IEC standards around the world. So here we have a test report that says that this technology of de-ionization was fully proven, and when you get the full report, it just says under discharge that it's not applicable, because it's not applicable. So company should be 9001, 14001 registered. It is NEC registered. It is approved by NATO. NATO has approved this technology. As I said, the technology of de-ionization is now accepted by the military. And there are many projects now developing around the world. And it's under this code, NCAGE code SFKU3, and you can look that up and see that. Underwriters Laboratory, I mentioned that. That is a product that's there. Because of Brexit, CE marking and UKCA. Before the crazy situation we had, fully approved in the Russian and the Commonwealth of Independent States. Before the Troubles, about 1.5 years ago, the technology was fully proven. in those markets. The good news is, as I said, it's a passive technology. It does not require power. And every part of the technology is actually ROSH compliant, no hazardous materials, and can be recycled. Of course, with technologies like this, when people hear it the first time, and when you see that video at the beginning of just the clear frenzy of lightning, it's difficult to understand that you can protect an area with such great power happening in the atmosphere. And so there is many documents about land-based, documents about marine-based, case studies from companies around the world that were being struck by lightning regular. And when the technology was deployed of de-ionization, that lightning strike effect did not come to their protected area. The graphene device here, this is the military one. There's some documentation on that, and so on. So now, just to finish this part of my presentation, because we nearly run into an hour, it's important to see that companies around the world have gone and done the due diligence. They've looked at this technology in detail, and they've then deployed it. I'm sorry, it's just under my black part at the top of the screen there. But this is a very successful story. This is a company called Silent Yachts. If you're at sea with a solar paneled yacht, you're a big red flag for lightning. And so traditional technology doesn't help the solar panels, because as you can imagine, if you have a traditional technology that a strike comes to, you are then bringing all of the other aspects to it. So Silent Yachts now deploy this technology on their fleet of boats. Of course, when you have some super yachts, this is a Mirabella 5 yacht, and you might just be able to see the dot at the top here, and there's a video on YouTube of the installation on these type of yachts. Again, a mast of this size, again, is a major target for lightning if you're the only guys at sea, or even if you're in the marina. So, this is a, very, very expensive yacht. And the owners of this yacht have taken the technology and done it. And in fact, in the UK market now, our distributors are selling this technology to some of the super yacht builders and other yacht builders across the UK. Catamarans, for some reason, get hit by lightning more than other vessels. But with a catamaran here, you can see the CMC is at the top here. It's earthed into the hulls, both because it's 2 hulls, of course, being a catamaran. Some you get trimarans as well, which have 3 hulls. And we earth below sea level using the sacrificial anodes that are down under sea, and we protect catamarans. Now get into the land-based assets. Petrochemical industries absolutely do not want to see lightning coming to them. Whilst it can be arrested with a Franklin rod or an ESE, you are still bringing all of those factors to it. So many petrochemical companies now around the world are moving to this technology of de-ionization. And remember that the de-ionization covers a large area depending on the device. And so by putting one device at the highest point, which is done in a site survey and plan, you can protect these tanks from any type of discharge. And that's an example there. So just go on from there. Telecoms towers, quite often you get affected by lightning. Surge protection comes in when strikes come on all sorts of different buildings and assets. Here we can see a couple of examples of telecoms towers. Corporate building. Now, corporate building, in fact, I'm hopefully working on a project now in the City of London who are looking to potentially deploy this technology. When you have a very large-scale corporate building, the Faraday cage that you may use, or the Franklin rods, or potentially the ESE, which may be less, you may need a lot of Franklin rods, as I said before, and every single corner, halfway down, may need a Faraday cage and so on. What we did on this particular corporate building is just put one device on, and it protects the entire building. So another fantastic thing about the technology is it does not interfere with any electrical signals. It's purely de-ionizing the atmosphere, as you know, because we've talked about the technology. There are no, power electronics in here. There's nothing that can interfere with radar. There is, to date, because we're deploying more and more, there's over 9 airports in the world now that have deployed this technology to protect their radar. So if you ever needed a reference, an airport is not going to put its radar at risk thinking that this technology doesn't work, because it fully does, and it's fully proven, as Nikola Tesla said back in 1916. And the step for the airports, which is a very important thing, as all these customers are shown now, is that the intelligence of the Storm 7 monitor now allows these asset owners to see what is actually going on. This is actually, the top one is in the capital of Paraguay, Asuncion. This is a FIFA football stadium. You see the floodlight tower here, and there is a video from the owners of this football stadium that is on YouTube and also within the Certec site. In fact, they had a bit of money. They decided, let's put one on every floodlight tower. And so we did that. It only really ever needed 2 devices, but so we have one on every floodlight tower, and it protects the facility significantly. Below here, this is America. So you know that if you're like anywhere in the world, if you're going to put a technology in, you need to make sure that you're going to protect all of these people that are watching a game. So the Great American Ballpark is a very, very famous ballpark in Cincinnati in the United States. We protect. You see these horror story videos that come up now and then when football players are struck by lightning, thinking they're safe. And if storms are around, they are definitely not safe, because I mentioned the bolt from the blue earlier, and the distance, as you saw in the video, of lightning. So these stadiums now have been protected for a long time. The stadium above 12 years, lightning all around it, but never any strikes to the stadium. Renewable energy. In a lot of places in the world, there are these little renewable energy type of power bases. And they become targets, and you can see here the technology deployed. It's a small one. It's a nano, 25 meters, completely protected technology. Now, everybody knows Ford. Ford is, one of the biggest manufacturers of cars in the world, as everybody knows. We protect this factory in Dearborn, in Detroit. It's a Ford factory. They did not want lightning strikes coming to them. They did not want to adopt ESE technology. And they didn't want to go with the chance of dissipation array technology also, because some of that technology requires, quite sophisticated designs compared to what you see on the left-hand side here, one capacitive technology protecting a large area of the site. Coal power generation, these big generation plants, they're big targets. There's metalwork everywhere. There's buildup of charge everywhere. And again, here in Taiwan, the chimney on the right is protected, and also the buildings. I mentioned mines. We have a video on this. This particular mine here, this is the communications tower. The CMC is, this technology is deployed at the top. It's protecting a large area of 120 meters around the mine. And again, this is for the safety factor of the miners, that when lightning comes, there's going to be no strike to the ground. I did mention military. This is the only slide I'm allowed to share. Everything's under non-disclosure agreement. The technology is not only moving to protect the land-based buildings, but also military vehicles now, and also military ships that are on the sea. So it's now coming to protect that, and there's a lot of technology development for these type of applications. What we have here is just a quick slide. Of course, solar farms, you already saw that with silent yachts earlier, and then you see the wind farms, which we're working on projects on there. And this one here is, again, there is a huge case study that's available to see. This is AES. It's in South America. It's a generation of energy plant. It's a huge, huge site. And this had hundreds of Franklin rods all over it. And The owners were, you know, the technology of Franklin rod was bringing the strikes to them, but they didn't want that. They wanted to move away from that type of technology. And so they installed 26 of these devices, which cover the entire facility. And since this technology has been deployed, the buildup of ionization does not occur in this area. Remember, if you look outside of this, of course, in further afield, the buildup of charge is still occurring. So, you know, the downstreamers take the path where the charge is the greater. So if you take away all of this ability to build up charge, you do not have the ability to strike. This one here, we're nearly finished on the slides, couple to go. This is an electrical substation called CEPM. The owners of this site, you know, requested that we brought our technology to them 10 to 12 years ago. You see just a few of the Franklin rods here. There were many that were removed. But they were suffering from the Franklin rods being struck by lightning. All of the surge protection was being also affected with some of the towers and things where strikes were going to different areas and sometimes not going to the Franklin rod. And they supply, I think it's something like 45,000 resort rooms in a holiday resort near to this substation. And they were losing power quite regular because South America has so many thunderstorms. So we went in, we deployed, which probably just about see there above my name, if you can see my name there, on top of the transmission towers, the technology. And since they've never had a lightning strike in 12 years. So I'd like to thank everybody to listening to that because it's an introduction to the technology. You can get more information from the websites that you can see here. You know, it's a great honor for me to be able to speak to the Institute of Engineering and Technology. And I'm going to stop sharing and I'm going to pass back to my colleague, Mike, for any questions that you may have. Thank you very much.
Thanks very much indeed for that, Stephen. That's been excellent. We've been very well attended today. That's great to see. And got lots of questions. Looks as though we've got some experts in the field, so that's brilliant to see that. First of all, I need to just mention people have put questions into the chat area. Maybe they missed the introduction, but please transfer any questions that you've got into the Q&A function, if you will, because I won't be able to download any unanswered questions from the chat function, and I will deal with the Q&A function first. And I can see that there's 55 questions in there. Not that we're going to get through those tonight, I don't think, but that's the first point. The other housekeeping issue is just to reiterate, and one or two people have asked, and I can see that some emails have even come through on my IET volunteer site, is CPD certificates that I said at the beginning are available from our website for the South Yorkshire Local Network. If you log on to there, you'll find the address actually in the chat function now. If you just scroll up to time 609 under SL, that stands for Sandra Lucy. She's actually put the link, so just copy that into your browser, and you'll be directed there in due course, and you'll be able to download your CPD certificates. So thanks for that. And before we start with any questions, I'd just like to mention about my faux pas in saying institute instead of institution earlier on. I'm very sorry about that. I'm a member of the Chartered Management Institute, and I always get them mixed up, so I really am sorry about that, and very embarrassing for the length of time I've been a member. So the other thing that just mentioned, somebody eagle-eyed, probably gone on to LinkedIn, I don't know, spotted that Stephen's only recently joined the institution. I hope that's part of my evangelisation as well for the IET, that I've been able to coax Stephen to join us many months ago, and it wasn't anything to do with the this particular presentation. So thanks for that. So let's get started, and we'll try and get through as many of these as we can. I noticed there's quite a few that have been answered actually through the course of Stephen's presentation. So I'll just start at the top, and this is from Barry. This may be a little out of scope. Any views on EMP protection, especially for PV cells and associated equipment such as inverters, increasingly a consideration? And he just went on to say, I mean EMP in relation to a nuclear explosion. And I'll, so how shall we protect PV cells? So I'll let you answer that.
Okay, so Mike, thank you for that, and thank you everybody for the nice comments that you're making. It's such a fantastic subject to be able to give a webinar on. That's a fantastic question as well, because EMP is a big issue. It's an issue that data centers don't want, for example, as well, because they don't want this electromagnetic pulse coming through the air to data centers. So what we're doing is we're making another big step this particular quarter. We're going to be working with what is going to be one of the world's biggest laboratories in Saudi Arabia, in Dammam. It's called the GCC Lab. Is for the whole of the Gulf states. And the Saudi government have funded this laboratory where we're going to be very actively involved, developing more, answers towards EMP and how that affects multiple assets, of course, obviously with the solar farms and so on. So we do have some early documentation that if you're interested, we could share. And we can talk about that as well. So there is documentation available about the effects of that, how to protect against it. But my feeling is that over the next 3 to 6 months, that will become significantly enhanced as we work with the lab.
Thank you for that, Stephen. I've got one. It's the same person, Barry. How come the charges split in the clouds, please, bearing in mind that same charges repel?
Say that again, Mike. Sorry.
Yeah. How come the charges split in the clouds,
yeah.
Bearing in mind that same charges repel?
Yeah, it's okay. So if you look back at the video earlier, the ionization is the ice crystals. Actually, the electrons are actually on the outside of an atom. Okay, and to get ionization, what happens is the ice crystals, though it's said, and the turbulence within the clouds actually push these electrons to become free electrons, and they're able to move. That's where you get the name free electron. And the charges then start to separate. So that's what happens in the cloud that was shown in the video.
Okay.
Can I just answer one thing, Mike? I saw it flash up on my screen. Somebody said, well, I don't think that, it will help much with EMP. In its essence, as a technology right now, a very good question to make and a point to make. What I didn't finish was at the GCC lab, we're looking at advancing the technology to be able to do in a different way with EMP. So it's not the individual device right now, but it's a technology development.
Okay, thanks very much indeed for that, Stephen. Are ESE accepted by the British standards?
The technology is not accepted yet by the British standards. And the reason it's not accepted yet is because the technology requires in BS 62305 a discharge, and this technology does not do that. And because it's not written into the standards, the technology doesn't meet the standard. The reason that I've joined IET, IEEE, SIGRE, all of these different groups is that I would like to be able to, and I've already got an open discussion at the moment, although we've not got too far yet, with British standards to say, look, please can we, it's good for everybody. Can we talk about this technology and potentially bring it into the standards? Because as you've seen by all the examples, it's completely deployed.
Okay. I think you've answered this about how much electricity power does a ESE typically use. I think that's a very quick one.
Yeah. Well, the ESE, is a different technology. It's actually, it's providing the upstreamer, so it's not the same technology.
Dennis asks, does a draining current have renewables potential use, i.e. could it be captured and stored?
You never know with anything. At the moment, the drainage current is only in milliamps. It's very small. So as we develop, so the thing about the company is we've taken this technology, which Nikola Tesla invented, to a modern day product fully deployed. We're looking at EMP, we're looking at all of the other aspects that you can do with it. But in its essence, the technology is there to protect, and we will develop on from there.
Oh, okay. Alex asked the question, I think the first two are related. How commonly used are the ESE and the DAS? And how commonly used is the CMCE?
Yeah. Okay. So if you look at those technologies, ESE has been around for a long time, and so has dissipation array systems. The one wonderful thing about this presentation today is that people were not aware of this technology. So the dissipation array system, you can see lots of pictures of different areas where that's used, and you've seen the way that these are constructed. And I know a lot of good companies out there, promote this technology. And with the ESE, this was invented in France. The French style of protection is to use this technology of, creating the upstreamer. And so it's been deployed for quite some time. What is happening now in the market, as the complete awareness of de-ionization of this technology is becoming available, it's expanding significantly, and we have projects across the world for entire substations now, entire plants. So it's gaining momentum. In the marine world, a trial was done with one of the big transport companies, I can't name them, out there. We did a 1-year trial on one of their huge container ships. It passed, and they're now going to deploy it. So what you're going to see over the next 12 to 36 months is a really significant growth in this technology, which I'm happy to say is patented by Certec.
That may well answer one or two questions later on, so thank you for that. Anonymous says, is the CMCE system recognised by IEC 62305-3? If not, is this something that you would think will be added to the IEC?
Yeah, it's a sort of little repeat. It's a great question because it's a key one, because we know that having British standards, having IEC approval is the right thing. So what I mentioned earlier, just to repeat myself, I want to work with these groups to bring the technology in as fast as possible because it's fully proven.
Okay. Neil asks, how dependent is this technology on the quality of the earth provision? I'm thinking of sites that are located on permafrost. Also, what RF footprint does the technology have with respect to impact on nearby antennae?
Yeah, what a fantastic question. So that's a big one to answer. What we do is the company has earthing specialists, okay, and we like to work with earthing specialists and companies around the world. So what we do is we do a complete soil analysis, and that soil analysis and the earthing side of it, we have solutions for, because no soil is the same around the world. So depending on what that is, the site survey determines exactly how you should earth and so on. Right.
Okay. I noticed that Anonymous has asked a rough estimate of how long the talk is. Well, the talk's over now. We're into. Sorry, I didn't pick that up earlier, but we will be carrying on with questions and answers probably for another 15 minutes.
Yeah, no problem.
And we will. Stephen has volunteered to answer any questions at the end, and we'll post those up afterwards. Thank you for that. Tom, are you able to tell us what materials the units are made from?
Well, they're made of different materials. It's another good question. The materials are fully recyclable. So depending on whether you need high temperature military applications, the military applications are made out of graphene, for example. Some of the super yachts want them to be stainless steel. So we have stainless steel ones. So it's a variety of materials that are used depending on the application. So it, depending on that application, it's different materials. But again, they're all environmentally friendly. And this wonderful device that you can see above my shoulder here is fully recyclable.
Brilliant. And Paul Mass here, what have you UL certified it in accordance with? That's underwriter's laboratories. So
yeah, it's the standard UL 96. I don't have the full details of that here, but we have a documentation showing what that certification is. So it's UL 96.
Yeah, I think we've answered the second part of your question, Paul. Barry, what is the bandwidth of the CMCE compared to the bandwidth of a lightning bolt?
Yeah, well, a lightning bolt is about 2 to 3 centimeters across. It's very small, and the CMCE, this de-ionizing technology, does not bring that to it. That only goes to Franklin rods or ESE or potentially other solutions. And the area of protection, as I mentioned, is up to 120 meters today with the technology inside the device.
Okay. How often should the LPS be periodically tested?
Great question. In the presentation before 2022, you would go out and do periodic testing. I mean, the whole market, in fact, the other company I work for, IPEC, do condition monitoring of partial discharge, and that is continuous monitoring. With lightning protection, now we have an accessory that allows you to test 24/7. And if you have a large site, let's take the AES site in South America, 26 systems are deployed there. Each one of those systems can have the accessory on it, and that can show back to your control room. And from a maintenance point of view, an insurance point of view, it can show you if you have issues or not. So the technology now is monitoring itself.
Okay, and there's a couple of questions on cost.
Yeah.
And it's one goes on to say, can this be put on top of a building and earth to the earth rod without any further tests for simple application?
Yeah. Okay, so that's the good question as well. Let's just cover cost at the moment. If you take I'm not going to talk numbers because there's a lot of barriers, but if you take into comparison that on the AES site there were 100 Franklin rods. When you think about the installation cost of that, the earthing cost of that, the factor it's not intelligent, the factor that you've got to actually periodically test all of your Franklin rods or your ESEs. That becomes very costly. When you put one of these devices in place and you condition monitor it, cost comparison is without a doubt there. And in fact, it becomes cheaper because you now have a permanent monitoring system year after year after year. And maintenance costs are lower, capital expenditure costs and operating costs are lower. And that's all part of the proposals that we do.
Okay. Jack's several questions here, but it is said right at the end, thank you very much for the wonderful presentations. How can we know the height and width or bandwidth of the CMCE to the lightning strike to enable to know how many can be deployed per electrical installation? Yeah.
Okay, so that's again a great question because how do you deploy this technology? Earlier on in the slides, I showed a very, very basic slide of a site survey. When we do them, they're much more in-depth detailed. But really what you do is, the most basic one is to look at a Google Earth picture of the site. That gives you the area, as long as nothing has changed. And then you look at the actual site drawings. Because one of the things we're doing quite a new number of projects now in Africa, is some of the sites have big trees next to them. And a tree is a major conductor of lightning. The sap within the tree builds up the charge and so on. So the way to answer that question of how do you know how many, where you should position and what coverage is part of that intelligence that you do by doing a site survey?
Yeah, same question. You've actually answered it there. How can it be made accessissible across Africa and Nigeria? So I'll skip that one.
Can I just ask you one question on that, Michael? Very, very interestingly, Siplat Energy in Nigeria have just deployed their first installation. We're protecting actually their head office first before the plant. And we've put a CMC 120 covering 120 meters with a Storm 7 in, and that is live now. And that's enough.
Great. And finally, from that same question, CPD certificate of participation, it's as I mentioned earlier, if you just look in the chat at the time 609 under SL, you'll see that there's a direct link to get your CPD certificate there. One here, has the technology being applied to hazardous areas?
Yes. Yeah, this is one of the major areas that we deploy the technology. You may have missed it, but in the slides, you can see the petrochemical industries. We protect a lot of petrochemical industries, AES, gas plants, oil plants, refineries. The hazardous areas are extremely interested in this technology, and it's being deployed. And we have case studies. Yeah.
Yeah. Paul's asked, have you presented any papers on the technology to the ICLP, the International Conference on Lightning Protection? Are there any hyperlinks to the papers that we could put up?
Yeah, another good question. Just a very quick snapshot. I joined the company just over 18 months, nearly 2 years ago. I found them on LinkedIn. They had nothing in Europe, Middle East, Africa, or Asia, and we've developed a significant network now. And part of our practices, like today, is to engage with all of these organizations and bring this technology to them. So over the next 1 to 2 years, you'll see a lot of events. In fact, I'm going to do one for the University of Birmingham via IEEE. That's going to be on the 24th of October in the UK.
Okay, a couple of very short questions. Barry, again, bandwidth of the artificial cloud ?
Yeah. Okay, so area of protection, we have a documentation on that of how that actually occurs. How can you prove that it protects 25 meters or 55 meters or 120 meters, which is a long distance? So the details that are contained within that documentation shows you how that umbrella of protection is calculated and how it's proven.
Brilliant. Zibias, would it withstand lightning if it happens?
Yeah, that's a great question. We get asked that question normally first. So what happens with the technology? And, you know, we're confident. It's never occurred, but we have tested for it. What it would then end up being like a Franklin rod technology. Okay, so it would dissipate down the earth into the ground. So there is a fall safe with it, but it is not a Franklin rod technology. But if it was to be hit, it would protect itself. You probably wouldn't have a device left, but the charge would go to ground.
Okay. Ian's posed a question here. I've noticed you've amended it later on, Ian, so thank you for that. What is the design lifetime of the DAS system?
Yeah. Okay. It's not a DAS. It's a the DAS is dissipation array system. We are not called that. I suppose you could. It's a slightly different terminology and different approach. The lifetime of the product, they come with a minimum of 5 years warranty, and we're looking to extend that at the moment. A lot of the products that we've got out deployed that have been out for 10 or more years. You know, if you're doing correct maintenance and your condition monitoring, they have a long lifetime, but it's a minimum of 5 years warranty.
Yeah, there's a couple of questions along the same lines here on this one. One from Chris here. What would happen is if an area of 1 square mile or more was protected, the ionization buildup in a cloud still exists. So would this mean that there've been more strikes in the surrounding area?
Yeah, that's a great question, because we get asked that, because we can have an industrial site that's fully protected and the one next door isn't. Does that mean that that outside of that 1 square mile, as you mentioned there, do we create more lightning strikes? And the answer to it is potentially yes. What the technology is to do is to protect a specific area. Charge builds up, so outside of that area, if there is no protection in place, there is a chance that a strike will occur. Now, what we put into the Storm 7 condition monitor is we've put in lightning detection technology. So what you will see, and I'm sorry I didn't have it to show you today, is that there is a report that says lightning strikes all around it. And that's very important for showing insurance companies, that you haven't been in an area, you've been in an area of lightning and you haven't been hit.
Okay, thanks for that. And Alex, I think that answers your question about diverting lightning to nearby buildings. John asked why so heavy, e.g. 1,200 kilograms, or is this a continental comma 1.2 kilograms in US Stoke English? Okay,
so as everything works, like mobile phones that were big boxes and that, the technology has come a long way. What we're doing is we're utilizing newer materials now that are lighter. Graphene, for example, is a significantly light material. It does have other characteristics about it. So what you'll see is that some of these products, when they're on top of a building, even at that weight, there's no requirement. Where it changes, what we've seen now, is in the marine world. In the marine world, if you've got a sailing yacht, you don't want something too heavy at the top of the mast, especially the racers in the sailing world need it light. So what we do is we're adopting, developing, building the technology for individual requirements that require different materials, different weights, different solutions. That's all part of the technology roadmap.
Yeah. Just for my own sake on that, Stephen, it suggests that it could be 1,200 kilograms. Or
no,
1.2
kg.
Yeah, I'm going to say that's over a ton.
Yeah, no, it's not 1,200 kilograms. No, 1.2 up to about 6.5, and yeah, the twin is a little bit heavier because the technology inside, the capacitors inside there, are heavier. They're a more powerful device. And again, we do, just one thing I never mentioned before, we do protect a nuclear power station in America. We're allowed to just say that. We're not allowed to say anything else, but we do.
Okay. And I noticed that another one about certificates, which I've answered earlier, and also several people have asked for a copy of the PowerPoint. It is being recorded, this this presentation, so you will be able to catch up later on the same site that I referred to earlier. Aidan, are surge protection devices required with this technology?
Yeah, you do require it in some certain areas, because we do put that in. That's all part of a master plan that we put together. You don't really need to have the surge protection in line with the device, but other areas of plants, we still like to have safety in place. So depending on the plan, we would advise on that as well. We do surge protection technology.
Yeah. Yeah. What are the advantages of graphene and twin devices? That's from Alex.
Yeah, good question. So graphene is a lighter material. It's extremely strong. This is what's being used in military applications right now. So the use of specialist materials is a very important thing as we go forward. So that's what we do with the materials. All of the material side of it depends what it is.
Yeah. How many other companies do or can manufacture these devices? I think you've answered this. It's coming from Brian.
Yeah, we are the world leaders in this technology, and we have the patents for this technology. I'm sure, like any other technology, somebody will come along one day with another device, but that's really where we are.
Okay. One here from Hayden. What's the lifetime of the products?
Yeah, 5 years plus, 10 years.
Okay.
But to be honest, we're going past those barriers now. Initially 5 years warranty, now moving towards 10 years.
Yeah. another one on installing surge protection. So go over. What's the effective coverage? This comes from Daniel. I think you mentioned 180 meters diameter.
Yeah, it's 120 meters of radius, so 240 diameter.
Next question from, that's anonymous. You've answered that one on replacements. Yeah, I think you've answered another one there. Here we go. David's asked, the test lab's results were clear that there was no discharge. What would have been the result of using a simple passive electrical field, minimizing dome instead of the Franklin rod, which is designed to maximize electrical field?
Well, if I understand that correctly, if we were to test it in a different way, well, what we have to do is test it in the way that a strike would occur, and that is that buildup of the electrical field, which would be with a Franklin rod, the ionization of the Franklin rod, and our technology, the de-ionization technology, does not allow that buildup at all. So you know, this is part of the process that we go through quite regular every day, the educational process of de-ionization, and why you do not have the effects that you would have with you know, the other technologies.
Yeah, I think you've probably answered this, but what about distributed assets such as power transmission lines?
We protect those already. One of the slides that I had at the end there was CEPM. The transmission lines we protect on top of those. You can see them on the towers. You know, it depends. Sometimes what asset owners are doing is they're taking critical sites. They may not want to put one on every single transmission tower, but they take the critical sites and they protect those where they see more, you know, electrical activity.
Yeah, there's been quite a few questions about what about areas outside the coverage of the unit itself, you know. So I'm just going to skip past those. Again, you know, we'll revisit this with your permission, Stephen, and just put that up on the website. So if I'm missing any questions here, please forgive me. We will answer them in due course. How is the monitor? This is coming from Ken. How is the monitoring system integrated? Is it accessible by the public, or can it be monitored, or can the monitoring be done by private control rooms?
Yeah, that's a great question. So the accessory now takes the data from the down earth cable, okay, and processes that, and also inside of it, it's got this intelligent for temperature, humidity, atmospheric pressure, you know, the distance of lightning strikes around. So obviously data is the normal thing in the world. You can have a secure network that this data goes into encrypted. You can have it localized, you can have it on your phone, your laptop. There's different protocols that you can take the data from, and over the next 1 to 2 years that will develop further and further. Things like Starlink, and you know, because a lot of you know, sites can be extremely remote, so you don't have, for example, Wi-Fi. You wouldn't have, you know, Bluetooth connections. So there's different protocols, and these are in development as well.
Okay. And there's one from James. I think we'll probably call it to a close, the questions after this one, because we've passed the time that you were presenting. So the questions are sort of supplementary after 7 o'clock when you stop presenting. So really appreciate all the questions that people have sent in. We'll do our best to make sure that we answer them in due course. But you know, you've rattled through these so well, Stephen. I really do appreciate you going through them, and I think you've answered most of the questions from what I can see. But James asks, have any installations been installed within Network Rail, which is obviously to home?
Okay, so that's these sort of questions are fantastic. This particular year, I did 4 seminars across the UK, one in Swindon, one in Falkirk, one up in the Midlands there. And this was really the introduction of the technology for the very first time into the UK market. And so where we are right now is we created significant interest in the technology. The only caveat has been that for British standards 62305, you need, the standard says it to take the strike. So a lot of the asset owners, and Network RAL would be a fantastic opportunity, is we're trying now to get some promotional sites in place. We're talking to the City of London right now for a very major building in London. So we're open to talk to the customers, try and put some sites in place and show this technology with the condition monitor working.
Great. Well, look, that's been a fabulous presentation, and some of the questions have been great, and thank you for getting to as many. I mean, I've sat doing presentations myself. There's no way I would have answered the number of questions that you've answered tonight. So thanks very much indeed for that, Stephen. And for all the people that have sent lovely feedback as well. I really do appreciate that, and it's been terrific that we've had so many that have attended tonight, and I appreciate that very much. So again, you can view it all over again if you'd like to, and appreciate everybody's input into making it a terrific event again for South Yorkshire local network of the Institution of Electrical Engineering and Technology. Thank you very much indeed, and good night.
Mike, I'll just say one comment finally. I know you're signing off now. Thank you very much for the huge crowd that we've had tonight. I'm here to work with the IET. This is a very important subject for all of us. The lives lost in the world, the buildings and asset damage is significant. So to everybody around the world that's listened in, thank you very much. You can contact me or contact Mike, and we will help develop this and perhaps bring some more webinars for the future. So thank you very much, everybody. Thank you. Thank you, Mike, very much.
Thank you.
I'll sign off now, Mike.
Okay, I'm ending the presentation. Thanks again.
Yeah, we'll have a chat tomorrow.
Okay, thank you.